Now, the next type of surface integral that we're going to look at is the surface integral involving a vector field. We're going to call this a flux integral. But before we start, let's just remind ourselves of a couple of things. If you have a level surface and you look at the gradient, so you take the gradient at a point on that level surface, what you're going to get is a vector that's orthogonal to the tangent plane. It's perpendicular. Now, and you can, and I've got a couple of pictures here. One, notice this one here, you have the vector pointing outward. It's orthogonal. But you could also have it pointing inward, like this one here. And notice the difference. This is the gradient divided by its magnitude. This is the opposite of the gradient divided by its magnitude. Now, the question is, well, how do we get that vector? Well, let's suppose that you have a plane, or not a plane, but a surface. And I want to write that so that it looks like a level, so that it presents itself as a level surface. In other words, maybe I'll do this. Let's do this. Let's just take the g of xy and put it over here with the z. Now what I have here is a level surface. That's a level surface, and I think I'll just call that level surface. Now, looking at this, I know that for that particular surface, z equals g of xy, if I take the gradient of this thing, if I take the gradient of this capital G, what I'm going to get is a formula for orthogonal vectors. So let me go ahead and do that. I'm going to go ahead and get the gradient. So here I go. And remember how this looks. The partial with respect to x, partial with respect to y, and the partial with respect to z. Okay? So this is my gradient vector. Now, I don't know the magnitude of that vector, but I can compute a normal vector. I can compute a unit vector by just dividing by its magnitude. So if I want to divide by the magnitude, what I would get, I would get this g of x, y, z, and if I divide by the magnitude, it looks something like this. What I get is this. I get negative g, and here's what I get. And then down here, the magnitude is going to be gx squared plus gy squared plus 1. Okay? Now, that right there is what I will call the unit normal vector. And you can see, this is what we're looking at here is this vector here. This vector pointing away like this. Okay. They're using capital N there, I use lowercase. Now, what we want to do is this. We want to consider a situation like just an application to help you understand surface integral or a flux integral. Imagine fluid flowing through some kind of surface. And I've got a picture of that here. And let's suppose that these arrows are pointing in the direction of the flow. And they flow out of this surface. And what we want to do is we want to figure out, well, how much fluid is flowing through the surface per unit of time, let's say. Well, what we want to do is to calculate that, and think about this. Think about this little shape here. We're getting the volume of that thing. Okay, so we're having this fluid go through here, and what I want to do is I want to get the volume of this little shape. Well, what I need to calculate the base times the height. Well, the base is just going to be the surface area on the surface, this little part down here. So I need this little surface area down here. But then I need to get the height. So it looks like what I need to do is I need to project this force, or this vector field, this vector, over to this vector that's orthogonal. Now, let me just say that, let's just suppose that vector that's orthogonal, I'll just call it V. And what I'm doing is I'm projecting this vector onto this v vector? Well, notice that's going to be f dot v over the magnitude of v squared times v. Okay, that's the formula for projection. Now let's take the magnitude of that. If we take the magnitude of that, then what we're going to get is f dot v over the magnitude of v times the magnitude of v, which is going to give us f dot v over the magnitude of v, because the magnitudes cancel there. Well, that is going to give us a unit vector. So this part right here, I'll just call n. Okay, so what I have is n, and there's my vector. Now that is going to be the height. So if you think of that as the height, then what we have is this. We have this surface integral, and we're going to add up. So what we're doing is we're going to add up a bunch of these. These little things right here, I'm just going to add up an infinitely many of these infinitesimally small little shapes. And what I'm going to get over this surface is I'm going to get the height times the area of the base. And the area of the base is ds. Okay. Now, this is just the general form for our surface integral involving vector fields. Now, let me see if I can simplify that a little bit. So, we've got this surface. And I rewrite this surface this way. And then I get the gradient. And in particular, so, and we know, we've already done this. We know that n is equal to negative gx squared, not squared, negative gy and 1, and we divide by the magnitude. Okay. Now, as far as ds goes, so that's the n part. Now, as far as the ds goes, well, the ds, remember, is the square root of gx squared plus gy squared plus 1 dA. Okay, so that's the ds. Now, we can put all this together, and look what we get. We get the double integral over this surface, and we're going to get f dot and then down here is the magnitude. And then up here, we've got and you notice that this cancels. So now let's see what we've got. We've got f, x, y, z, dotted with negative gx, negative gy, and 1 dA. Now, so this simplifies a little bit, but still we're not finished. Remember, we want the z values on this surface. So what I'm going to do, I'm going to go back and rewrite this as f of x, y, and in place of z, I'll put g of xy. That's what z is. And then I'm going to dot that with negative gx, negative gy, and 1 dA. And this is this is the form that we're going to use to evaluate the surface integral with a vector field. Now, so let's look at an example. Let's suppose I want to evaluate this surface integral. And I've got this surface with z greater than or equal to 0. And this is what I've been given. I want to go from here and evaluate this integral. So I've been given the vector field, and I've been given the surface. Now let's see what we can do with it. Okay, so first of all, I won't bother with the bounds yet, but here's what I have. I have 3x, 3y, and now in place of z, I'm going to put 9 minus x squared minus y squared, because that's what z is. Now the rest of it, what I'm going to do is I'm going to look at this level surface. This level surface is going to be z plus x squared plus y squared minus 9. Okay, so I bring everything over with the z. Now I'm going to dot my vector field with the partials now. The partial with respect to x, the partial with respect to y, and the partial with respect to z. And then I have the dA. Okay, so there's what we have so far. Now, at this point, I just need to, I need to figure out what the bounds are, but I think before I do that, I'll go ahead and do this dot product, and I'll get the bounds here in a minute. But here I go. I got 6x squared plus 6y squared plus 9 minus x squared minus y squared. Okay, so I just dot product the whole thing. Now let's see what we have. We have 5x squared plus 5y squared plus 9 dA. Okay, just putting everything together. Now, at this point, it seems obvious to me that the easiest course of action is going to be to view this in polar coordinates, because when you think about this surface, where it intersects the xy plane, it intersects in a circle of radius 3. So that tells me right away that probably my best course of action is to view it in polar coordinates. So here I go. Let me just write this. I've got 5r squared, because x squared plus y squared is r squared, plus 9. Then I've got to do an r dr d theta. You always have to have the r dr when you're working with polar. Now, when I look on the xy plane, this is my region that I'm integrating over. Well, so what it is, or in other words, it's r squared equals 9 or r equals 3. So as far as r goes, r is going from 0 to 3, and then theta is going from 0 to 2 pi. Okay? Well, at this point, we just have to integrate this, and then we have our surface integral.